Hi, welcome to this lesson on calculus, applications of the first derivative. So again, let's recall, what is the first derivative? Well, essentially the first derivative of a function at a point or in an interval tells us how the function changes with respect to that independent variable that we are working with. So the first derivative of a function f can tell us three main things. The intervals of where the function f is increasing. So, for example, if you look at this function f, can you see where it's blue, the curve is increasing. So you can imagine on the xy axis, as your x increases, your y values are increasing. Then suddenly the y values are decreasing here in this red interval and then begin to increase again on the blue interval. So if we examine the tangent lines on these blue points here on that interval, the tangent lines, which are the gradients, right? The gradients of the tangent lines, which are the first derivatives, these are always positive numbers. These are positive gradients. So therefore, when the first derivative is greater than 0, so that inequality, when that's true, then the graph itself we can say is increasing in nature. Then we have intervals of decreasing, which is exactly the opposite of increasing. So again, here on the xy axis, where you have red here, the graph is decreasing, and you can see the gradient of this tangent line is negative, whereas the gradients here were positive. So again, gradients translate to first derivative, and therefore when the first derivative is less than 0 on that interval, then we say that the original curve of the function f is decreasing. And then lastly, we get stationary points, which can also sometimes be referred to as turning points when they actually turn. And that's when the graph reaches either a minimum or maximum turning point at a stationary point, and the gradient there will just be a single horizontal line where the gradient is 0. So when the first derivative of a function is equal to 0, those are stationary points. So let's have a look at an example. Find the intervals of the function f of x equals x minus 1 all squared plus 3, where f increases, decreases, and if there are any stationary points. Okay, so this function here is a quadratic function, a parabola, and it's actually in the completed square form. So recall the completed square form gives you the coordinates of the turning point, a times x plus p all squared plus q, right? So, or x minus p rather, so that we have the coordinates being p, q. Okay, so to find the intervals and the stationary points, we first need to calculate the first derivative. Okay, so to do that, I'm first going to expand out this product. So it's going to be x squared minus 2x plus 1, and then plus 3. And then adding that together, I get x squared minus 2x plus 4. Then I can use the sum and difference rules along with the power rule and see that the first derivative is 2x minus 2. So for stationary points, we set the first derivative equals to 0. Those are the easiest to find. It's a simple equation. So 2x minus 2 equals 0, and we find that x equals 1 is the solution there. So at the point x equals 1, if we evaluate the y value, so if we plug that in, we get 3. So the coordinates is 1, 3. That is the only stationary point of f. Okay, so it actually turns out that that stationary point is the turning point on the parabola. Okay, so I've gone ahead and drawn the sketch of that curve, right? So this function here, f of x, that is x minus 1 all squared plus 3. Okay, so where is it increasing and where is it decreasing? So for increasing, you need to set the inequality as follows. The first derivative greater than 0. So now we have a linear inequality. So to solve this linear inequality, we need to isolate for x and then get x by itself. So here we get x greater than 1. So on the interval 1 to infinity, so from this value but not including it onwards, can you see that the graph itself is increasing? And that's because the gradients of the tangent lines on that interval is positive. So therefore the graph is increasing on that interval. Similarly, for decreasing, you solve the inequality f prime x less than 0. So doing the same algebraic steps, we get x less than 1. So on this interval here, right, so from negative infinity all the way to 1, we can see that the graph here, red, is decreasing. So as you come from negative infinity to positive 1, your graph just keeps coming down, 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 down. It's decreasing until it reaches the minimum turning point, then increases again. So all the gradients here of the tangent lines are negative. Okay, because they're sloping left to right. Okay, so that is a nice way that we can tell the intervals of increasing and decreasing and stationary points using the first derivative. Let's have a look at another example. We want to find the intervals of the function f of x equals x cubed plus 3x squared minus 9x plus 6. So this is a cubic function. And again, we want to see where f increases, decreases, and any stationary points. So again, we need the derivative. I can use the sum and difference laws along with the power law, and I get 3x squared plus 6x minus 9 for the first derivative. So stationary points, easiest ones to do. We solve f prime x equals 0. So I need to equate this to 0. I have a common factor of 3, which I've pulled out, and then set it equals to 0. So therefore, I factorized the quadratic expression inside there, and now I've got just the 0 property for algebra, where I can set each factor equal to 0. So I get x equals 1 or x equals negative 3. So what are the coordinates at that point? Well, if I plug in f of 1 here into this original expression, I'm going to get a y value of 1, because I'll get 1 plus 3 minus 9 plus 6. So I'll just be left over with 1. And then f at negative 3, if I put negative 3 in here, I'll get a y value of 33. So these coordinates here, 1, 1, and negative 3, 33, these are the only stationary points of this cubic function. Now for increasing and decreasing, notice that we need to set f prime x greater than 0 for increasing, but now this is no longer a linear inequality. It is a polynomial, a quadratic inequality. So now there are steps that we need to do in order to solve the inequality. Okay, just can't rush and put in these values here and say, oh, there it is. No. Okay, this is a polynomial inequality. We have a procedure to follow. So we find our critical values. That's when it's equals to 0. So basically our stationary points. We saw that was at negative 3 and 1. Now, because it's strictly greater than 0, I have open dots here on my number line. Then I test the sign in between each region. So if I take x equals 2, for example, and plug it back into this original inequality expression, I'll get a positive number. Same thing here. If I take 0, for example, and I plug it in here, I'll get a negative output. And then if I take something less than negative 3, like negative 4, I'll get a positive output. So again, from this number line, and the original inequality was greater than 0, so that's this region here, then the graph of f of x, the original graph, will increase. So it'll increase, right, on this interval here from negative infinity all the way to negative 3. And then it'll start up again at 1 and increase again. The same thing for decreasing. We do the exact same algebraic routine, but instead now for a decreasing interval, it is less than 0. Okay, so solving for less than 0 will give us this region here, which we found in the previous question as well. Okay, and again, it's decreasing on x's from negative 3 to positive 1. So we'll learn the exact process of sketching a cubic function, but I thought let me show you what it looks like now so you get an idea. So we have our stationary points. There's one, negative 3, 33, and 1, 1. And then we saw from the interval, from negative infinity to negative 3, the graph was increasing the whole time. So it's just going up, increasing. It reaches a stationary point and then starts to decrease on this interval, negative 3 to negative 1. Reaches another stationary point and then turns again and starts to increase again. Okay, and you can see the tangent lines, the gradients, they 0 at the stationary points. They are negative in this interval, negative 3 to 1. And when the interval is between negative infinity and 1, or negative 3 rather, the graph is increasing. And then from 1 to infinity, the graph is increasing again. All right, so that is the first derivative. Its applications mainly are to tell us where the graph has stationary points and where the graph is increasing or decreasing. All right, so knowing that knowledge now, we're going to do some practice questions with it. I'll see you in the next one.